Okay, we're ready to move on and look at homogeneous coordinates, which are probably the most important mathematical technique we have in computer graphics. We can look at it in a number of ways. We're going to derive it as sort of coming out of what we're doing, trying to build up representations and changes of representations. It's where we go in for three-dimensional problems, we find out that we'll be easier to work with them in 4 dimensions, for two-dimensional problems to work at them in 3 dimensions. So we're going to introduce homogeneous coordinates. It'll come out of how we do changes of representation, and we'll see that we'll have a representation that will allow us to distinguish between points and vectors, that issue we brought up at the end of the last lecture, very naturally and very easy. In fact, homogeneous coordinates has a very, very deep basis mathematically. That's one way to do it. On the other end, people look at it as the big trick in computer graphics. Like once you know it, you know how to build a graphics system and make everything work. We'll be somewhere in the middle, but in fact, it is the reason why we can do transformations that are so crucial and do them in the pipeline and do them very, very rapidly. And if we didn't have the homogeneous coordinate representation, our graphics systems would look very, very different. So let's start with this. Suppose we go back to our representations of both points and vectors in a frame, using alphas for the representation of a given vector and using betas for the representation of a point. We could look at it in the following way. And here's the trick, a little bit of the trick. Remember a while ago we said, even though it doesn't make sense to multiply a point by an arbitrary scalar because a point has no geometric properties, it's just a location. But if I define 0 times a point to be the 0 vector and 1 times the point to simply leave the point alone, then I could write the following. I could write alpha 1 v1 plus alpha 2 v2, alpha 3 v3. You may as well do this just in 3 dimensions. It'll work in any number. And what if I tag on a 0 here? We're going to do this purely formally. We're going to say, okay, here's a product of a 1 by 4 times a 4 by 1, and that should give me a 1 by 1, which is just going to be v. And what do I do when I take this? See, notice the transpose here that's converting this row into a column. What do? I multiply corresponding elements and add them up. So this is alpha 1 v1 plus alpha 2 v2, alpha 3 v3, plus 0 times p0. Oh, but wait a minute, we just decided we were going to call 0 times a point the 0 vector, so this just adds on the 0 vector, and the 0 vector plus any vector leaves it alone. So therefore, I get alpha 1 v1, alpha 2 v2 plus alpha 3 v3, and it's just an alternate way of writing it down. Now the benefit comes here. Consider a point now. It's p0, the origin, plus beta 1 v1, beta 2 v2, beta 3 v3. What if I write it this way, using the same row matrix times a column matrix, so it's beta 1, beta 2, beta 3, and I put a 1 here. Now, what does this happen? What happens here? By just simple matrix algebra, I multiply corresponding elements and then add them all up together. Beta 1 v1 plus beta 2 times v2 plus beta 3 times v3 plus now this 1 I put here times p0, but we agreed to say, okay, 1 times a point is a point. So this comes out to be p0 plus beta 1 v1 plus beta 2 v2 plus beta 3 v3, which is precisely our way of representing a point. So if we worry now only about the representation, because both of these, this vector and this point, are in the same frame. So if we understand what the frame is, I say within that frame, the vector is represented here as with the 4 scalar constants, alpha 1, alpha 2, alpha 3 at a 0, and the point is represented by beta 1, beta 2, beta 3. And here's the key issue. It has a 1 here. So what does that do compared to that last example I had in the previous lecture where I said, oh, this is confusing. I don't know which are points and which are vectors. Now I have a representation in which every vector always has a 0 for the 4th coordinate, and every point has a 1 for the fourth coordinate for three-dimensional points and vectors. If you did this in 2 dimensions, you'd have an alpha 1, alpha 2, and a 0. But we want to work in 4 dimensions so we can represent 3-dimensional entities, and then 2-dimensional entities we'll get by just setting alpha 3 and beta 3 to 0. So this is a wonderful representation that we can manipulate, and we can manipulate it because we've gone away from the abstraction of using these abstract basis vectors and use their representation, which is just 4 scalars for each of the vector and the point. And now this enables us to actually now use only algebraic operations with 4x4 matrices and 1x4 or 4x4 row matrices or column matrices. And this is what's going to make everything work for us. And now let's look at a few examples in this lecture, and then in the next lecture we'll start doing this all with transformations, or this will give us transformations. Okay, so as I've said, this is the key to everything by just going up to using, if you're in 3 dimensions, don't use 3x3s, use 4x4. And the pipeline works this way. The pipeline you'll see is because you can chain or concatenate 4x4 matrices together. That's what the pipeline is doing. It's multiplying a bunch of 4x4s. Now this issue of the 0 and the 4 and the 1 for the fourth component, which is called a W component. We say we're in XYZ W space. The way we started is we said, okay, we're going to make this fourth component 0 and 1. Does this always have to be a 1? No, it's always a 0 for vectors. We like to start with it a 1 because it's mathematically easier to use to do things that way. It'll turn out when we get to talking about perspective transformations, the 1 will be changed to another value other than 0. So we'll have a non-zero W, but everything will come out just fine. So give me another week and we'll get to that. So for now, and if you're using orthographic projections that are sort of default that we started with, the 1 will always stay as a 1 and you'll be fine. It's only when you start doing perspective that you do a transformation and the 1 can change to a non-1 value, and we'll see it. It's not going to be a problem to deal with. Also note that because the hardware is doing this, you get to build it directly into the hardware. So you're not really, when you try and multiply 4x4 matrices together, that should be the amount of work if you did it in a brute force way. It's always, for multiply 2 n by n matrices, it's n cubed operations. That's not going to really be true in hardware because you're going to really, this is so important that it's actually built into the hardware essentially in parallel. So you can think of it as, oh, I'm multiplying these 2 matrices together, but that's one instruction, so don't. So everything has been parallelized in there using these 4x4 matrices. Okay, so let's go back to the problem of how do you change first coordinate systems, and then we'll talk about how do we change frames. So in a coordinate system, all we can represent are vectors, and what I want to do is now take it and represent it. Now here I've gone back to 3 dimensions. I'll change this back to homogeneous coordinates in a few minutes. But here I want to make the point is, suppose you have 2 different basis systems. So you have the same coordinate system, and one of them, the basis is V1, V2, and V3, and in the second one, the basis is U1, U2, U3. One of them could represent, say, the object coordinate system. The other might represent the camera coordinate system. So it says if I have a given vector V, it could be represented in either one. In one, I'll get an alpha 1, alpha 2, alpha 3. And in the other one, because it has a different basis, I'll get 3 different scalars, which we'll call beta 1, beta 2, beta 3. So how do I go back and forth between the two? Well, let's look at it this way. That if I look at the first basis vector, v1, v2, v3, here's the other basis vector. This might correspond to doing something like a rotation, that I rotate the first coordinate system to get the second, and here's my arbitrary vector that can be represented in either one. But if I ignore my arbitrary vector for a second and say, wait a minute, let's look at the basis vectors in the second system, u1, u2, and u3, and say, well, each of those is just a vector in the original coordinate system, so I should be able to represent it with three scalars. So that says, well, look, u1, the first basis vector in the second system, has three constants I'll call gamma 1, 1, because it's going to refer to the first basis vector, times v1, gamma 1, 2, v2, gamma 1, 3, v3. Likewise for the second one, it has a representation in terms of v1, v2, v3, and likewise so does u3. Well, that's going to define a matrix, a 3 by 3 matrix with these 9 coefficients in it, which I'll call just M here. And in fact, if you use this matrix M, and let me go back a second, and I make a column vector out of u1, u2, u3, and I make a column vector out of v1, v2, v3, if I put all of these nine constants in a matrix M, this is just saying that this column is equal to M times this column. It's, AX equal B. It's a very, very simple representation, and that's what we have here. Have to be a little careful about the order and the transpose. If I write them this way, then the representation in the let's see which system. The representation in one system is given in terms of the representation in the other by just multiplying by the transpose of this 3 by 3 matrix. Very, very straightforward. It also says a couple of other things. Since these constants, these 9 constants, can be arbitrary, it says there are 9 degrees of freedom corresponding to 9 constants when you do a change of coordinate systems. Now let's apply that same argument to changing frames. Now what changed in frames is I have a fixed origin, and I can talk about points, and how do I change in the frame the representation of both an arbitrary vector and the representation of an arbitrary point. So we're saying here's 2 frames. They can have 2 different origins, and they can have 2 different sets of basis vectors for the underlying coordinate system, and a point could be represented either in the Q0, U1, U2, U3 frame, or in the P0, P1, P2, V2, V2, 3 frame. Well, what happens? Well, I can write them given the algebra that we used a couple of slides ago and say, okay, I'm going to write the basis vector u1 in terms of v1, v2, and v3, just as I did a couple of slides ago, because this is only referring to the vectors, and I get 9 constants, gamma 1, 1 through gamma 3, 3. But I also want to know, how do you represent the new origin in terms of the old origin? Well, the way I'm going to do that is to say there's a vector that carries me from this origin q0 to p0, and that vector has a representation in either basis. So I could say then, if I do it that way, then the new, I'll say q0 is the one. I want to go from p0 to q0. There's a vector, and that vector now has 3 coefficients that multiply the basis vectors v1, v2, and v3, and potentially something that multiplies p0. But we said because these are points, I can only multiply by 0 or 1, so actually gamma 4, 4 has to be 1. Has to be 1 here. So now I have a matrix that will carry me back from a representation of a point in one frame to a representation of a point in a second frame. And what's even better than that is that what's the difference if the thing I'm multiplying m by I'm going to actually transpose m. If what I'm multiplying by is a vector, not a point, well, it says, see, if I multiply by something here, gamma, by something that has an alpha 1, alpha 2, alpha 3 here, that's a point, then it multiplies by this constant, and down here times 1 times the point. That's correct algebraically. But if it's a representation of a vector, there's a 0 in the fourth component. So it multiplies a constant times the first vector, a constant times the coefficient of the second, a constant times the coefficient of the third, then 0 times the point, which leaves me with a vector. So the algebra all works in 4 dimensions, and or another way of saying it is there's a single matrix with 12 degrees of freedom, because there are 12 possible coefficients here, that will always carry me from a point to a point or a vector to a vector, and my job is to fill in these proper elements, and that gives me the desired change of representation. There's a couple of numerical examples in the notes that will show you how give you a little more proof that this is going to work. And this is just saying the same thing. If you have a representation of 2 different frames, the representations look like this, but alpha 4 and beta 4 are going to be either 0 or 1. 0 if we're dealing with vectors, and 1s if we're dealing with points. And in any case, the change of representation can be written as this matrix multiplication using 2 column matrices for these 2 representations. So that all works very, very nicely. It's again why the homogeneous coordinates is so wonderful and easy to use. There's a couple of other things that follow from this, and we'll see much more when I talk about specific implementations of this for doing the standard transformations like rotation, translation, scaling, and shear, and later on for doing projection transformations. But these are called affine transformations, and they're not simply general transformations in 4 dimensions, because a general transformation of 4 dimensions would have 16 elements that you could choose. This is special because we can only adjust 12 of the elements. But once we've said that, we've had 12 degrees of freedom, and certain very nice things happen here, is that every affine transformation corresponds to a change of frames, and that change of frames, because of the only 12 degrees of freedoms, actually can be shown fairly easily that it preserves lines. And what's the importance of that? This is key to everything, because we're working with vertices. How do you define a line or a line segment? You define it with 2 vertices. So when I want to transform a line, I don't have to worry about how does every fragment that goes on that line get transformed. I don't worry about that. What I'm going to transform are the 2 vertices that determine that line, or line segment more often, and then I could fill in the points in the middle through the hardware, and just send the vertices down the pipeline rather than worrying about all the points along the way. And that's what really, you put this all together, and that's why graphic systems, pipeline architectures are so fast. They only need transform the vertices and pass those vertices through the shaders. The shaders carry out these affine transformations. Okay, so finally, the 2 that we care about the most, and this is what we're going to be looking at over the next few lectures, are the world and the camera frames. They're the obvious one. I need to go from one to the other, and we will generally, in any version of OpenGL, start with the world or object frame, and then we're going to use an affine transformation, or equivalently a 4x4 matrix, to change that. Now, initially, when you want to go from this world frame to the camera frame, they start off as being the same. The default in OpenGL. And let me back up and say one thing. You get to pick everything you want. In WebGL and all the recent versions of desktop OpenGL, these particular frames are not hardwired in. The camera is sort of hardwired in, but it's very helpful to think at least in terms of an object frame and a camera frame, because any other way I think you go about it, it just gets too confusing. They seem very, very natural to at least have these 2. Okay, so everything I say here, you're going to have to create these matrices or take the matrices out of the package that we've given you, but we're going to follow this notion of having what's called the model view matrix, which is going to be the matrix that carries us from the world representation or the object representation to the camera representation, and that's going to be one of 2 key matrices that we're going to be working with throughout this course, the second one being the matrix that does the projection. Now, each of these matrices corresponds to a transformation in affine coordinates or in affine spaces, initially these frames start off the same. So the matrix M we've been talking about is an identity matrix. So let's finish with a very, very simple example today of what M would be to do something. So suppose you have initially, sort of the Y and the YC here, and the X and the XC here are supposed to indicate that these two frames have the same origin and they're lying on top of each other. So initially this is corresponding to M being an identity matrix that the camera and the object frame are the same. But suppose you have a bunch of objects that are distributed in space. Some of them are in the negative Z space, some of them are in the positive Z space. The camera in WebGL is fixed to be by default at the origin and it points in the negative Z direction. So if I want to see all these objects, I have two choices. I could move the camera away from the object, so I look at them from further back. I can move them down this positive Z-axis, or I can move the objects in front, push them in front of the camera. Now, our view of life is a little different. The artist's view is you move the objects. The physical view is you move the camera or the viewer. So what we're going to do is move the camera back away some distance d. Now, that separate is equivalent to saying, what are you doing in terms of the object frame and the camera frame? Well, I'm moving them apart by a distance d. What does that correspond to in terms of the matrix? Well, if d is a positive number, I'm going to move back some negative, some minus d here. But look at what that does. That, if you work out the mathematics, that matrix is going to multiply some x, y, z, w representation. What does it do? Well, if you multiply this out, this is 1 times x, 0 times y, 0 times z, 0 times the w component. So it's leaving the x alone. Okay, let's back. We had a little glitch there. So if we multiply this out, you multiply by x, y, z, w. The x is unchanged. The y is unchanged. What happens to the z values? The z becomes z, x times 0, y times 0, z times 1, minus the w. Now, if this was a point, the w component would be 1. It would be z minus d times 1, or z, and then the result is z minus d. So it's the same as subtracting d off of each z component, which is essentially moving the objects or moving the camera, depending on how you want to look at it. And in fact, this is our first example of what's called a translation matrix, which will develop in more generality in the next lecture.